All right, welcome back. All right, so we're going to deal with an object sliding down a ramp with friction. We will assume that it will get moving, so mu sub k equals 0.3. So as this thing is sliding down the ramp, energy will be lost. It gets converted into heat, which is just basically energy being transferred, thermal energy being transferred. And thermal energy is just dealing with the particles are moving faster inside the box or in the ramp. But the total energy is going to get transferred outside the system. So we start out again with work non-conservative is equal to the change in energy. We are dealing with a box sliding down the ramp here. And so if we did the force diagram, we have weight acting down, normal force acting perpendicular, and then we have friction acting up the ramp. As before, the normal force is not doing any work because it's perpendicular to the motion. Friction, however, is doing work. And because it's opposite the direction of motion, it's doing negative work. And so we have negative, so this is the non-conservative force, dot delta x, is equal to E final minus E initial. This is negative friction times displacement. Times the distance it actually travels. I've already taken the vectors into account. The fact that it's moving this way, but the force is that way. They are in opposite directions, 180 degrees between them. So it's a negative is equal to E final minus E initial. And what we need to do is, so therefore my initial energy minus friction times the distance it travels, the distance it goes down the ramp, is equal to E final. So we're going to end up with less than what we started with because we're subtracting some. This becomes kinetic initial plus U initial minus F delta X is equal to kinetic final plus U final. 1/2 mv initial squared plus mgh initial minus F delta X is equal to 1/2 mv final squared plus mgh final. And let's see if I can write that so it's actually legible. 1/2 mv final squared plus mgh final. Slightly more legible. So as this thing is sliding down, so we need to know a couple things here. Initial speed, let's throw that in there. So initial speed will start at 0 meters per second. Again, we're going to assume that it is actually sliding. The height, well, it's a 37-degree angle, and I have a 15 here. So the height, this distance right here, is going to be the hypotenuse times the sine of 37 degrees, which should be 9 meters. Roughly 9. It should be a 3, 4, 5 triangle, so it should be 9, 12, 15. I'm going to make h is equal to 0 at the bottom. 0 meters for the purists. And we do need to still break weight up. So doing this method with energy is not necessarily the most efficient way of doing it, but we can do it anyway. And so I know that down the ramp is W sine theta. Into the ramp is W cosine theta. So the normal force and W cosine theta are going to be equal to each other. And so this becomes, that's 0. My final height is 0. And since I'm down at the bottom, I'm going to have to sit because I'm tired of slouching. So I'm left with mgh initial minus mu sub k times the normal force, which is mg cosine theta. That's the normal force right there. Times delta x equals 1/2 mv final squared. Let me write that up there. So I have mgh initial minus mu k mg cosine theta times delta x equals 1/2 mv final squared. I now have I have 3 terms here. Mass gets canceled out from all of them because I have the same factor in each of them. So mass cancels out, mass cancels out, mass cancels out. And so VF, which is what I want to figure out, how fast it's going at the bottom, is equal to 2 times G H initial minus mu K G cosine theta delta X square root. So that's the square root of 2 times, well, we can factor G out also, but anyway, 9.8 times 9 minus 0.3 times 9.8 times cosine of 37 degrees times the distance it actually travels, that's 15. And now calculator exercise, 9.8 times. So this is 88.2, and this is 0.3, 9.8 times 37 cosine times 15 times. This is 35.22. Subtract times 2, and I get the square root of 105.96. And so I get 10.294 meters per second. That's how fast it's going at the bottom. Now, using energy here is not necessarily the simplest way. F equals ma would work also. This would be a chapter 4 problem or 5 problem. However, if I threw bumps and curves into it, just imagine doing the ski problem with F equals ma. That would be incredibly hard because the normal force direction, how much weight is actually in the direction of acceleration, is constantly changing. So energy in that type of situation is really convenient. Energy also comes back into play after we deal with momentum, and you'll watch those videos and no doubt rejoice constantly. So that is a problem with friction in it.